Hi, everybody. Good morning. My name is Vikram Hosakote. I'm a software developer at Cisco Systems. This is a talk about how we enable jumbo frames in OpenStack, and we were able to resolve a lot of issues, packet drop. We were able to improve efficiency. We were able to reduce latency, and also instances were faster when jumbo frames were enabled in OpenStack. So let's just dive right in. So the agenda is, so we'll talk about what's MTU, what is IP fragmentation, and then jumbo frames in OpenStack. So how can we enable jumbo frames in OpenStack? What are the config files we need to update? And then the use case I tested. What are the tests I did before jumbo frames and after enabling jumbo frames? And then an interesting concept that I learned in my testing is the Path MTU Discovery that OpenStack doesn't fully support. So I'm going to talk about Path MTU Discovery as well and how we did manually, and then some advantages, disadvantages of jumbo frames. And finally, question and answers. I'll be around after my talk and be happy to answer any questions. So what is MTU? So as you may already know, MTU is the size of the largest packet that can be transferred by an interface without fragmentation. So that's mostly the default behavior of any switch or router. Like when we boot a switch or a router, it doesn't expect to receive bigger packets. The default behavior is it receives the default size of 1500 bytes, and then it just transfers it through the outgoing interface. So there are three ways MTU is decided or set by the interface. It's fixed before transmitting data. Ethernet, you can either configure it or use a GUI and do it in the case of UCSM that I'm going to show in my next slide. It can be negotiated during handshake or connect time. So some routers don't know the MTU of the other end of the link. So it's going to ask what's your MTU when it negotiates the session. And some protocols actually can determine the MTU dynamically as the packet travels through the path. As the packet enters each interface, it's going to find out the MTU and then decides if it has to be fragmented or not. Default is 1500 bytes. Jumbo is 9000 bytes. This size is the payload without the header and the trailer in the packet. So this is a very generic IP packet. So we have 14-byte Ethernet header, usual 20-byte IP header, and then there's a 20-byte dhcp header, and the payload itself, and then the checksum of 4 bytes. So when I was doing my self-testing, it was mostly TCP packets, but I observed that the interfaces were very busy just receiving packets, and they were not doing any deep packet inspection or anything. So we found out that if the interface receives less number of packets, even if they're big, the drop was less. So IP fragmentation, from the Wikipedia link, it's a process that breaks datagrams into smaller pieces so that packets can pass through a link with smaller MTU than the original datagram size. And then on the receiving host, the fragments are reassembled. Both fragmentation and reassembling both are supported by IP. It, however, adds additional processing on the interface. I'll talk about it in my next slides. That's just the the packet capture, how the don't fragment bit looks in the IP header. So depending on what that's set to, the interface or the networking stack decides if it has to fragment the packet or not. So don't fragment. If it's set, it doesn't fragment. If it's not set, then it fragments. So this is a fragmentation packet. Packet that's going to be fragmented. So in OpenStack, it's not very straightforward. There's no CLI to do it. We had to update a bunch of config files and restart dhcp agent and Neutron server. So basically 3 files. In Neutron conf, enable global FizzNet MTU as 9000, and then advertise MTU true. This is optional if the DHCP server or a router advertisement needs to advertise MTU to the interface, then that has to be set to true. And then update OpenVSwitch agent.ini with the right bridge mappings. The bridge mapping has to match the name of the network that has MTU enabled, 9000 MTU enabled. And in ML2, we have to also mention which networks must have, what networks should have what packet size or MTUs in physical network MTUs. And then finally, Path MTU is 9000. So when that's set, Neutron is going to check if each path in OpenStack, if each hop in the path in the OpenStack layer has 9000. If not, then Neutron itself fragments it before it sends to the interface. So that's actually, we found out that that's actually quicker than making the interface fragment. If it's a virtual interface. In an SRAOE case, the interface is pretty fast doing fragmentation and reassembling as well. There's another option where we can make the DHCP server send option 26 to the interface and make the interface know at boot time or when it receives an IP address from the DHCP server that what's the MTU of the interface. So the DHCP server is going to set the MTU of the interface. And MTU values only apply to new network resources. So if we change the MTU of a network, the subnets, ports, and routers created after that will have the MTU applied. But any older subnets, ports, and routers created on the same network will still have old MTU. So that's actually a good enhancement. And we talked a bit about it in the Neutron IRC channel. They said they're planning to add it so that the moment we configure MTU, everything, old ports, old networks, also get the new MTU value. And that's deprecated. Network device MTU in Nova.conf, that's deprecated in Juno. My use case was pretty simple. Boot an instance, create a Cinder volume using Ceph backend, attach the volume to the instance, SSH into instance, and write lots of data into the volume, and measure traffic drop on the Ceph nodes. So I observed that as I was writing a lot of data in the instance, and I was checking traffic drop on the Ceph nodes, we found out that the interface itself was not actually walking deep in the packet. All it was doing was just busy receiving packets from the incoming queue, and it just handed over the packet to the Ceph mon that managed Ceph control plane and handling the packet. So when we increased the MTU, the number of packets received by the interface was very less. However, each packet was big. It was fine because the payload was anyway handled by the upper layer, which is Ceph mon, which is I think about TCP. That's the way we set in MTU in the UCS MGUI on the VNIC template. This, however, applies to older interfaces and networks and subnets as well. This is through the Cisco UCS MGUI. And we also had to enable Jumbo at a global level as well, so that all the blades connected to this UCSM system, get the Jumbo MTU on all of their VNICs. And this is how we tested Jumbo MTU. So in the output of a couple of Linux commands, we can check in IPA. We checked at the interface level on the Fabric interconnect, and then we did a ping. Ping as an option -S, where we can specify the size of the packet, and also -M that has 3 options: do, want, and don't. So when we say do, we make the sending interface not fragment. So the ping is going to fail if there's no Jumbo MTU. So -M has to be do in order to prohibit fragmentation, in order to send large packets. Path MTU Discovery. There's a lot of text here. This is not fully supported in OpenStack. We had to enable it on each hop in the path. So basically, the way it works is it sends a don't fragment bit during negotiation, and the receiving interface is going to send an ICMP back. And an ICMP is IP, so the sender will know from the reply that the receiving interface supports Jumbo or not. So there are 2 types, type 3, code 4. So that means fragmentation is needed. So that means the receiving end doesn't have Jumbo. So that way the sender itself fragments and avoids sending big packets and waiting for the receiver to fragment. So this way it's going to repeat until the destination IP address is reached at each hop on the network. And at each intermediate point, it's going to receive the ICMP reply back, and it's going to find out what hop has the least MTU in the entire path, and every hop on that path is going to agree to that least MTU. And this is the last slide. So I did see a lot of advantages and disadvantages as well. Obviously, greater efficiency, lesser packet drop, interfaces process fewer packets. The disadvantages, it affects per packet processing a lot. So if the interface has to walk deep into the payload, which is 9,000 bytes, then it becomes slow, even when Jumbo frame is enabled. Actually, if there's DPI, deep packet inspection, the recommendation is to not use Jumbo frame. It also depends on where the packet is walking up to in the payload. Bigger packets will increase lag and latency, of course, because they're huge on the link. They're traveling as big packets, and at every hop, if they're dropped, they need to be resent by the sender. And I saw the last disadvantage in my testing, the packet corruption. So even if 1 bit is corrupted in the entire 9,000 byte packet, TCP is going to retransmit the entire huge packet. And just corrupting 1 or 2 packets will make the link congested in case of a virtual interface. For SRAOV, I didn't see corruption causing congestion because it was physical interface, but I didn't corrupt a lot of packets for SRAOV. So SRAOV is pretty good as far as packet corruption causing huge retransmits. That's it. I can answer question and answers after the session.